realizing there are higher layers in the wireless stack that are equally important and that deserve, of course, considerable attention. So wireless engineers are clever people, but however clever they are, there's always demand for something better than what they're currently producing. So we've been fortunate going back for all the way to Marconi 120 years ago that we've had a string of really significant and brilliant developments. So let's just go through some of these. Marconi presumably started by sending wireless messages across the room or across his lab. But he had the vision that if you could do that, why not across the English Channel? Why not across the ocean? And in fact, 1905 was the first, I think, the first transatlantic wireless communications. Reginald Fessenden famously on Christmas Eve, again, right about that time, 1905 approximately, people listening to wireless for Morse code suddenly heard music. Must have been an incredibly startling event. Lee DeForest, the 3-element vacuum tube. Carson was a mathematician at Bell Labs and during the First World War invented single sideband. Major Edwin Armstrong, a string of huge developments in wireless that we're all familiar with, culminating in wideband FM, which years in advance of Shannon theory was the first coded modulation scheme. In the 1970s or 80s, Engel and Frankiel at Bell Labs, the concept of cellular telephony, of course, digital communications replacing analog communications, so low cost, great flexibility, the ability to do extremely complicated signal processing. And then, you know, about 20, 25 years ago, all of the work on multiple input, multiple output wireless, which multiplies spectral efficiency with no extra transmitted power. Wonderful invention. Okay. So historically, there's been a new generation of wireless every 8 or 10 years. Just as a personal aside, you know, in an era where the public and most engineers and scientists believe that we're progressing technologically with lightning-like speed, 8 to 10 years seems to be an awful long time to introduce a new wireless technology. After all, Thomas Edison in 1978 started his research and development on an electric lighting and electric power distribution system. And 4 years later had the world's first electrical power plant operating in Lower Manhattan. 4 years to do everything. So I sometimes wonder if we really are in such an age of technological innovation, but I'm optimistic that such things can still happen. So each of these generations involved some sort of disruptive technology. Obviously, if you had an analog handset, when things went digital, it suddenly became obsolete. When things went spread spectrum, obsolete. OFDM was introduced in 4G approximately 10 years ago, made spread spectrum obsolete. And now in 5G, the enabling physical layer technologies, 5G has been starting to be rolled out over the past year or so, mmWave and massive MIMO. And 6G, as you can see, I have question marks after, but I will tell what I believe are the trends in current research and development and make some assessment. So John Smee of Qualcomm in a blog, or you can find it online, defined the 5G technology by sort of 3 incremental things and 2 rather revolutionary things, massive MIMO and mmWave. So I'm going to talk subsequently about just where do massive MIMO and millimeter wave sit in 5G at present. How are they doing? So let's move on here. So my esteemed colleague, Ted Rappaport at NYU, of course, is justifiably credited with really introducing the concept of mobile millimeter wave communications. Experiments outside in streets of Brooklyn some years ago first showed that, yes, there actually may be, contrary to what many people thought, the possibility of doing mobile communication at millimeter wave frequencies, which is, all right. So let's look at the positive aspects of millimeter wave. Well, increasing your carrier frequency, say from 3 gigahertz to 30 gigahertz, automatically creates 10 times as much spectrum. And spectrum is a valuable resource. We have what we have. We can never create more of it. The wavelength, as the carrier frequency goes up by a factor of 10, the wavelength is 1/10 of what it was before. And one advantage, it means that for the same physical size of a antenna dish or a antenna array, the angular resolution of the antenna array increases by a factor of 10 in both directions. And this issue of blockage, basically when you increase the frequency from the 3 to 6 or below 6 gigahertz band, electromagnetic waves don't like to try to penetrate walls, foliage, human body. So this is, of course, a negative, but proponents have also said the same thing can be a positive aspect. You can have neighboring cells at millimeter wave, and now guess what? The interference is reduced among them by having gone to a higher frequency. Okay. Some negative aspects of going to millimeter wave, as I said before, blockage by walls, foliage, human body. The very fact that the wavelength is now 1/10 of what it was before means that it's a rather subtle effect. Sometimes people say that there is a greater attenuation as you increase frequency. Well, that can happen just because of interactions of electromagnetic waves with water vapor and oxygen and other molecules. But apart from that, if it were a vacuum, nothing like that happens. Attenuation is due entirely to spherical spreading. There's nothing special about millimeter wave versus lower frequencies. The whole point is, though, if I maintain the same directivity of my transmit and receive antenna, when I increase the carrier frequency by a factor of 10, the physical size of these antennas for the same directivity is reduced by a factor of 10 in both directions. So as a result, the collection area of my receive antenna is reduced by a factor of 100. And so I have to make up for that if I want to maintain the power aperture product. So I could increase my transmitted power by a factor of 100, but that simply is can't be done. So you say, why not just maintain the same cross-sectional area, collection area of my receive antenna as I go to higher frequencies? Well, the difficulty there is it now becomes much more directive, the receive antenna, than before. So if it were a dish, I have to very carefully mechanically steer it the proper way because it is such a high resolution antenna, or I have to employ a phased array and electronically steer it. So you see right off the bat, just to maintain what you've done at the lower frequencies, you have to work for it. The other aspect is that if you have mobile users, essentially the frequency response of the channel between the users and the base station it can change significantly every time the user moves a half wavelength or more. Well, if for the same speed of the user, say walking speed, then the channel changes 10 times as fast at these shorter wavelengths. And so if I'm doing wireless, and that's which requires somebody, either the users or the base station, to actually estimate the frequency response of the channel, I have only 1/10 the time I had before. So these are some of the disadvantages of mobile millimeter wave. Okay. Well, the big problem seems to be blockage. It's basically still an unsolved problem. Here's, so Professor Panwar at NYU, my colleague, has done some research with his students. And so basically, blockage is a big problem. So if you're milling around among people, moving automobiles for various densities of base stations, you get blockage, and it happens pretty frequently. And yes, I could, in principle, add more and more base stations, or they tend to be called access points when they get smaller and smaller. But that's an expensive solution. And the fact is, you still will have blockages, and they can last for significant periods of time. So if you're doing some critical application, gaming or telemedicine or driving automobiles from the cloud, or just watching video, ordinary coding can't correct errors over such intervals of time. And the problem just hasn't been solved yet. Now, that said, I don't want to be negative about millimeter wave. It's just that it's there, it's got to be used. That spectrum must be used. Wireless engineers and scientists are clever people. I think they'll eventually solve problems. Okay, let's go to the other technology for 5G, massive MIMO. The essence of massive MIMO is this: you replace an ordinary 4G base station. What it has is 3 120-degree antennas, and each of these 120-degree antennas spews out power indiscriminately in that 120-degree sector. Massive MIMO uses many small electronically controlled antennas to actually direct focused beams of data simultaneously to many users. The beauty of this is every user is served at all times and all of the time frequency resources. And so, why don't the signals interfere with each other? Because they're focused. So terminal 1 gets substantially what's intended for him without interference from the data streams to the other users. So this gives incredible spectral efficiency, 10 times better or more than 4G. And in the end, it's exceedingly simple. However, the execution is not simple. We'll have something to say about that. You can do power control for the first time in an effective way, which you can't do in 4G. And so users on the edge of the cell, and that's like just the geometry of the circle, you can give them extra power and still good service. And finally, it's a green technology as well. So just a few weeks ago, my eye was caught by a press release from Nokia, and or some record 5G capacity gains. And so these items, my bold type, caught my eye: 3 gigabits per second total downlink cell throughput, massive MIMO. So the proponents of massive MIMO have for years said that you could get this sort of operation. Naturally, I was very curious as to exactly what they were doing. There's more than one way to use an antenna array. This, by the way, is the Nokia AirScale 64-element antenna array, and it has 64 complete uplink and downlink electronics chains. And this whole unit is exceedingly compact. It's about 2.5 feet on a side and weighs something like 50 kilograms. It's more compact than these 120-degree sector antennas that it replaces. So when massive MIMO was first proposed 15 years ago, people said could never be done. Tower top electronics was considered a dangerous concept. Base station antennas were precious and expensive things, and but all of this, in fact, can be done. Now, the question is, what were they really doing here? I made some inquiries, and in fact, they're using a method called grid of beams to direct information beams simultaneously to multiplicities of users. We'll go into a little bit what that is. But the story is it falls short of the original and continuing vision of massive MIMO in a rather big way, even though it's a significant achievement. So what are you really looking for in massive MIMO? Well, many more service antennas than users, multiplexing beamforming, and to do this, to send these information beams simultaneously over the same resources to many users, the base station needs to know the frequency response of every channel between every one of the, say, 64 service antennas and every one of the 10 users. Okay, and the essence is to actually directly measure this frequency response. We call this closed loop beamforming. The other aspect is the time division duplex using the same band of frequencies on uplink and downlink is the only way to go with massive MIMO, because it lets you have as many service antennas as you want with no extra training overhead. The alternative is frequency division duplex FDD. I'll have some things to say about that subsequently. And then other features that you look for in massive MIMO, I mentioned power control, sophisticated beamforming beyond, say, just a maximum ratio beamforming, the possibility of variable length slots, high-speed users, the channel changes very rapidly, so you should put a relatively small number of users in short slots and then long slots for many more low-speed users. And so it would appear that nobody who is providing massive MIMO 5G service are doing all of these things yet. So we have a long way to go. It isn't that there are fundamental technical issues, it's economic issues and maybe perhaps to some extent political issues as well, business issues. So let's expand a little bit more on some of these issues we discussed. So open loop, so what is grid of beams? Grid of beams is, say, if you took the 64 element array and just tried to form 64 beams. Technically, this can be done by taking a 2D FFT, essentially. These 64 beams, then what you do is you send a test signal through each of the 64 beams, and then each of your users reports back on the uplink which beam was best for him or her. And that's what you go with. All right, that's the idea. And it's as opposed to closed loop beamforming, which I previously described. The problem is when you do this open loop beamforming, you're making assumptions about the ideal behavior of your array, and you're also assuming line of sight propagation, which of course most of the time doesn't hold. So it will work for a while, but as you add more and more base station antennas and make the array bigger and bigger, the performance will fall off, and that's completely unavoidable with grid of beams. And so that's why we emphasize direct measurements of the channels and doing closed loop beamforming. And now time division duplex permits unlimited numbers of service antennas. You have reciprocity between up and down links. So each user can, say 10 users can send 10 orthogonal pilots among themselves, and your base station antennas can each estimate these 10 frequency responses. And by reciprocity, the base station now knows the downlink frequency responses. Reciprocity. FDD, you simply can't do that. You use two different bands of frequencies for up and downlink, and generally they have nothing to, the frequency responses of downlink have very little to do with frequency responses of uplink. So if here we had, say, a 4 millisecond slot, so here the users went through 1/2 wavelength every 4 milliseconds if they were going 35 kilometers per hour. And horizontally, we have the number of active users that you can get the channel information for before within this 4 millisecond slot. Roughly you spend 2 milliseconds to get this CSI, channel state information, and then 2 milliseconds for sending data. And here we have the number of service antennas. Well, with TDD, yes, we ultimately are limited in the number of active users we can serve, in this case, something like 56, but we can have as many base station antennas as we want. FDD, you see, we're limited both in number of terminals and in number of base station antennas. Now, unfortunately, 3 out of the 4 carriers, though there's since been a merger, so I suppose it's 2 out of the 3 carriers, have only FDD spectrum in the most valuable sub-6 gigahertz spectrum. And so with this situation, the United States is doomed to inferior service in its most valuable frequency bands. And this is not a technical issue. This is economic issue and a question of how much demand is there, or is there going to be, for high throughput, very, very supremely reliable service. This is what will ultimately drive the adoption of massive MIMO in its most preferred form in the sub-6 spectrum. So question is, can massive MIMO be useful for millimeter wave? Well, let's just look at some numbers here. So here are 5 FCC auctions within the last 5 years, some of them rather recent. And let's just look famously in 2015 in the 1.5 to 2 gigahertz band, a total of 65 megahertz of spectrum was auctioned. This is something like 10 old-fashioned analog TV bands. A total cost, this was cash payments from Verizon, AT&T, and so on, of $45 billion, $690 per hertz. Incredible. And so then there was an auction of 600 megahertz spectrum a couple of years later, $270 per hertz. Now let's look at what happened, and then let's look at what happened when 27, 28 gigahertz millimeter wave spectrum was auctioned. A total of 850 megahertz, so 10, 12 times what we had before. But guess what? $700 million, 83 cents per hertz. And the most recent millimeter wave auction, over 3 gigahertz, 37 to 47 gigahertz, $7.6 billion seems like a lot of money, but $2 per hertz. So a factor of 100 or 300 or 400 with respect to sub-6 spectrum. So sub-6 spectrum is always going to be the most valuable spectrum because the wavelengths are relatively long, but not too long. And it has great penetration and can provide great service. And so this is really where massive MIMO can pay off because the spectrum is so expensive. Millimeter wave, as we've seen, is relatively cheap and numerous. And already just to maintain power aperture product, you need phased array technology. You're not even attempting to do anything like massive MIMO here. You're just trying to maintain the status quo of 4G. And again, if you wanted to do massive MIMO, you may only be able to serve 1/10 the number of mobile users at a time that you could have served in sub-6 spectrum. And so real considerations. So let's move on from 5G. So here is a possible future application. I have little doubt that young people 10 years from now, or whatever the technology is developed, are going to wear augmented reality display devices, which by then will be unobtrusive and effective and lightweight. They're going to wear them all the time. It will be just like now they're downstreaming our videos virtually all of the time. And this is going to be one of the most important parts of their lives, and they'll be willing to pay any amount of money for this type of service. And so I've always thought in these terms. I did these slides nearly 20 years ago when a director of research at Bell Labs had been approached by, it was somebody from Verizon or AT&T, to find out what did Bell Labs have in mind for the year 2020. And these were the slides I came up with. So this on the left, this is a ancient warehouse in Ostia, which was the ancient seaport of Rome. It's now outside the Rome airport. Suppose you had an augmented reality device, which in real time could render this as it would have looked 2,000 years ago, with all of the trees and sky and comrades in the picture. I mean, incredibly difficult computer science problem. I don't think the computer science is going to be available to do this for another 10 years, but really terribly staggering wireless communications requirements. People project 3 gigabits per second per user, sustained throughput, 10 millisecond latency. So imagine you have hundreds of people at a time at one of these sites wanting this service. I don't believe this can be done with any 5G technology, not even massive MIMO in its current, or even in its fully developed form. So we need a 6th generation of wireless, and people have thought, and irrespective of the applications we have in mind, there'll be plenty more coming along we haven't envisioned. So the question is now, what's going on in research for 6G? I hate to say the United States is behind in this. So Oulu University in Finland announced a year ago or so a 600 million euro 5G research effort lasting for, what, 7 or 8 years. We have nothing, I've not heard anything on that scale in this country. In the autumn, China announced a national R&D initiative for 6G. We have no such thing in the United States. Okay, so this is now speculation, but a lot of people are speculating, and you can see a lot of papers where people discuss such ideas. It seems whatever it's going to be, 6G has to be 10 times better than 5G. This has always been the historic requirement of a new generation of wireless. We need it 8 to 10 years from now. The problem is, 8 years ago, when people were starting to do R&D, in fact, development for 5G, we already had massive MIMO and millimeter wave waiting in the wings. Right now, we have no surefire physical layer technologies ready to go. Nothing. So yes, there are candidate technologies. Terahertz, very obvious, new forms of massive MIMO. Others pin their hopes on AI, machine learning. I think those have their uses. I tend to think they are good for things where our conventional techniques are not so good. So classically, of course, modern AI you can give it 50,000 photos and sketches of a dog, and you can give it 50,000 photos and sketches of a cat, and AI can actually come up with an algorithm that can reliably discriminate between dog and cat images. And if I had to solve that problem using the sort of stuff that I like to use, mathematical techniques and statistical methodology, I couldn't solve that problem. Another class of problems where our sort of conventional analytical tools fall short is when there are really strong nonlinearities in the system. So whatever we've done, I don't believe we've ever made much, we engineers or scientists or mathematicians have ever made much headway on nonlinear systems. And so these are the types of things where I would be looking for AI to bring breakthroughs, but I could be wrong, of course. All right, I've already said the research problem, but there is some research going on. Let's talk a little about it. So terahertz is an obvious thing to think of. Go from 30 gigahertz to 300 gigahertz. So Ted Rappaport is already doing experiments with his students up to frequencies as high as 240 gigahertz, propagation experiments in the lab. So obviously, This is going to give us 10 times as much spectrum, just as millimeter wave gave us 10 times as much spectrum compared with sub-6. But it comes with all of the negative aspects of millimeter wave. I need not repeat those. Some new ones, it's difficult to generate RF power at those frequencies. But these can be solved. This simply requires device people, transistor people to solid state people to get to work on it, and people are getting to work. There is a positive aspect, though, that these very short wavelengths, so at 300 gigahertz, you truly have a wavelength of 1 millimeter. So people have suggested some really interesting applications. True precision localization of the handset. Things get better and better as the bandwidth of the signal that you're using to do the localization gets smaller and smaller. Because of the short wavelengths, for instance, a half meter by half meter array has a 2 milliradian cross range resolution in the X and Y direction. So this opens the possibility to doing things you would not consider possible at lower frequencies, imaging, for example. In fact, who knows, maybe the applications, not necessarily a two-way communication, may be the most exciting thing ultimately that comes out of terahertz, but we'll have to see. There's certainly some considerations as far as communications researchers. I mean, if spectrum is so cheap, it doesn't pay to even meter it, then you're not going to want to use complicated communication schemes, multiplexing and all. Why not just give each user her or his own dedicated spectrum and make life simple for yourself? It always pays to go after the inexpensive and simple solutions first, and then when demand builds up, you then resort to the complicated things. So new forms of massive MIMO. So these fall in sort of 4 different areas. These actually overlap to some extent, but one is the idea of intelligent reflecting surfaces. So you'd like the effect of having a large array, but you don't want to actually have huge numbers of actual transmit receive electronics chains. So the idea of an array, an enormous array, because remember now, if this is a 1 meter by 1 meter array and wavelength is a millimeter, then a half wavelength, well then with half wavelength spacing to fill in this 1 meter by 1 meter array calls for 4 million antenna elements. And so the thought of having 4 million independent electronics chains at the transmit and receive side for this is daunting. But instead, if you have a surface in which you can locally alter dielectric and magnetic permeability properties of elements on the surface of the array, and if you illuminate this array just with a dumb high power RF source that reflects RF power off the intelligent surface, then you can control the reflected surface pretty much as you want. And so in terms of implementation, this of course has real possibilities. Does this open up any new possibilities, however? Another thing is just literally surround the user if he's in a building with antenna arrays on floor, ceiling, walls, or if he's out on the street with conformal arrays over all of the skyscrapers. So wherever you are, you're surrounded by antenna arrays. This again has very interesting research issues that need to be elucidated, and which will determine, of course, what new things one can do with this. I mean, one of the things is that technically speaking, you're always going to be in the near field of some of the antenna arrays, which means that instead of the wavefront being approximated by a plane, it actually is over a sphere. So you can't neglect the curvature of the field. Cell-free massive MIMO. I'll discuss that as well as holographic MIMO in the next 2 slides. So as I say, these are going to keep researchers busy, and researchers are looking at this. But of course, we don't know yet whether these things individually or collectively will have the impact of, let's call it, classical massive MIMO. Okay, so let's move on. So cell-free massive MIMO, the idea here is instead of covering a city with thousands of hexagonal cells, each cell containing a concentrated massive MIMO array, instead over the entire city you put 100,000, 1 million access points, wherever you can put them. Randomly, or in each access point could have a single antenna or multiple antennas. And of course you need power and backhaul to some central point for every one of these access points. But in principle, every user in the system is served by the principles of massive MIMO by all of the access points, even though some will be more useful for a particular user than others. Okay. And this has some advantages over cellular massive MIMO. Shadow fading diversity. The problem with cellular massive MIMO is I'm in a cell and surrounded by 6 other cells, so I have choice of 7 cells to get service from, but I may have blockage or bad blockage or shadow fading instantiation from each of the 7 base stations. But if instead there are hundreds, or I'm inside of 100 or 200 access points, shadow fading diversity is improved. The other aspect is under line of sight conditions, because of the wide angle spread of all of these access points with respect to a user, it may be possible to send not just one, but a multiplicity of data streams to each user. And this could in fact be the way to get this 3 gigabits per second required for AR. Okay, holographic massive MIMO. Well, the idea is ultimately you have a large, you replace a large antenna array, which at terahertz, as I said, would have thousands, hundreds of thousands, millions of elements, with a continuous radiating and recording surface. So no discrete antennas at all. And of course, the precedent for this is optical holography, where you illuminate some 3D object with a laser. You also have a portion of the laser to provide a reference beam. You actually take the sum of these two, the reflected field and the reference field, and take the magnitude squared, and when your photographic emulsion records it, you capture the phase because the cross term between the reflected and the reference wave retains phase. And so actually it's as if you froze the complex valued reflected field in this plate. And then when you illuminate it, you actually see a lifelike 3-dimensional virtual image. Okay, so in principle, of course, this could have implementation advantages for terahertz, because you could never do optical recording of this sort with discrete arrays of optical antennas. It would take 10 to the 11, 10 to the 12 antennas and electronics chains for a typical hologram. A more fundamental question is there any fundamental advantage in being able to, on transmit, control the electromagnetic field, or on receive, to measure the electromagnetic field on a scale smaller than a half wavelength? So there are fundamental issues here, there are implementational issues, but in the end, we don't know what the impact is going to be, okay? Let me talk about one final topic. We mentioned applications. How about wireless power transfer? So this, I'm in fact spending some of my efforts supported by our loyal industrial affiliates at NYU Wireless. I'm actually tackling this far-fetched and risky research. And of course, if it can be solved, incredible payoffs. What if you could wirelessly power drones or operating room instruments and devices in a hospital, or a factory full of robots, okay? So tremendous implications if it could be done. People have looked at this for many years, and the question is, why do I think that further progress is possible? Well, there was a big surprise 12 years ago. A group of researchers at MIT did a very simple experiment. So here was a coil, which they drove with a 10 megahertz continuous wave signal. And here was another coil several meters away, and they're lighting up a 60-watt light bulb here. And so the astonishing thing was, and this is what astonished the whole world, was they achieved 40% coupling, 40% efficiency in transmitting the power. They published their paper in Annals of Physics. I believe this is where Einstein published some of his most famous papers. Now, what's the lesson here? Well, there was no new physics or mathematics involved. So when I visited one of these researchers, I believe it was Corrales at MIT shortly after this announcement, he said that one could explain 90 or 95% of the effect just by old-fashioned circuit theory. So this thing acts like an air core transformer, but of course an ordinary high-efficiency iron transformer has a coupling coefficient of, say, 99%, meaning that the secondary intercepts 99% of the magnetic flux created by the primary. Here, the coupling coefficient is 0.2%. Yet, and here's the equations very simply derived from circuit theory for the received power divided by the transmit power. And so if this coupling coefficient kappa is 0.002, but the Q's ratio of reactance to resistance of the two coils are each 1,000. So you take 2 times 10 to the minus 3 times 1,000, and this product becomes 2, which when you substitute in gives approximately this efficiency. So this goes to show that, you know, you can have the physics and the mathematics complete for a particular phenomenon, and people still don't understand it. There are still discoveries waiting to be made. My first boss at Bell Labs, this was in 1995, was Jack Saltz. Some of you may know him. And Jack had a favorite saying, which is that no engineer ever creates any new mathematics. Any mathematics an engineer utilizes has always been done somewhere in some other form, perhaps by somebody else, okay? So there are lessons here. So if somebody says, we looked at this, we no understand the physics, we've done all the mathematics, it can't be done, you should take another look, which is what I'm about doing. So what can we do? This experiment, by the way, this was roughly 3 meters, 30-meter wavelength. So this was 1/10 of a wavelength transmission. Okay, we want to transmit many wavelengths. So what can we do? Well, there was a famous researcher at Bell Labs in 1943, Sergei Shelkunov. He is credited with having developed in the 1930s coaxial cable. In a paper in 43, Shelkunov showed, in fact, that the traditional gain expression for antenna arrays, which says that gain increases linearly with the number of antennas, is not a fundamental result at all. And then, in fact, in principle, you can do considerably better. Jerry Foschini was one of the pioneers of MIMO, and I met him on my first day at Bell Labs in 1995 when he told me about his work on multiple antenna wireless. So he and Mike Gans published an internal memo in 1995. Let me just read it to you. For example, consider a transmitting horn antenna, 10 wavelengths on a side, located in outer space aimed roughly at the Earth. With a 1 wavelength diameter super gain antenna on Earth, it is possible to receive virtually all of the power radiated by the horn antenna. I mean, this is just startling. We've never, anybody who's ever worked with wireless has never seen anything like this. And it's not at all clear when you read this, how does it function? It's saying that this receive antenna can basically suck all of the power out of a transmit antenna, though the transmit antenna is, say, 1,000 miles away. So would we call this spooky action at a distance? No, it has nothing to do with quantum mechanics. It's just old-fashioned circuit theory combined with electromagnetic theory. And superconductivity is all about placing antennas close together. Ordinarily, well, this close together proximity gives strong mutual coupling, which ordinarily we try to avoid by putting antennas at least a half wavelength apart. And so over the last 70 years, 75 years, people have re-examined this concept of superdirectivity and largely discarded it, because to make it work, you have to feed enormous currents into the transmit antenna. If there's any resistance in the metal of the transmit antennas, you have huge resistive losses. Locally, you have incredibly intense reactive fields. Reactive field, it's a bit like feeding a sine wave current into a capacitor. So every half cycle, you feed power into the capacitor. Every following half cycle, it returns the power. But again, nobody's ever proven that superdirectivity can't be done. So this has implications both for telecommunications and power transfer. Ostensibly, it looks like power is much more difficult because you can make telecommunications work with nanowatts or picowatts. Here we're looking for 100 milliwatts or more. So definitely seems more difficult. But for telecommunications, you have to have wideband operation, okay? Power transfer, I only have to make this superdirectivity take place at a single frequency. And then again, to do any interesting multiplexing with MIMO, you need to create degrees of freedom, a lot of degrees of freedom. But for power transfer, you're sending power, say, to one user, and degrees of freedom are largely irrelevant. Okay, so interesting to keep in mind. Old-fashioned network theory of the type that hasn't been taught in most US universities for 50 years is how you approach this. So here, for instance, I have say, an array of antennas that's trying to either transmit power to a single antenna or to receive power from the single antenna. But whatever goes on, this whole system looks like, guess what? An old-fashioned electrical network with an impedance matrix and an admittance matrix, okay? And circuit theory is then how you approach these problems. The electromagnetic theory tells you numerical values of all of the entries of the huge impedance matrix that characterizes the system. So here I have a theoretical calculation, a linear array of 10 antennas that's trying to transmit power to a single antenna 5 wavelengths away on the axis of the linear array. And I have power transfer efficiency as a function of antenna spacing in half wavelength units. So when I space my antennas, my 10 antennas, each a half wavelength apart, I get about 0.5% efficiency of power transfer. All right, now notice I shorten the spacing to 1/10 of a wavelength, and guess what? The power transfer efficiency has improved by a factor of 5. So this is the regime of superdirectivity. Okay, enough said about that. Just some conclusions, and then I'll take a few questions. So again, to have a new generation of wireless, you've got to have a breakthrough at the physical layer. 5G is being rolled out now, and it depends on millimeter wave and massive MIMO to make physical layer breakthroughs over 4G. For mobile users, stationary users don't have this problem. You can perch antennas high enough up so there's not blockage. So service has been millimeter wave fixed access to homes, for instance, has been done by Verizon at 28 gigahertz. But if you're trying to serve mobile cellular users, you've got this blockage problem that really needs solving. And massive MIMO hasn't reached its full potential, but where it will have the biggest impact is the sub-6 gigahertz band. As I said, a huge obstacle is the fact of the pervasiveness of FDD in the United States. Whatever we do, exciting new applications will necessitate a new breakthrough. If not, think of the alternative, the end of 120 years of progress in wireless communications, beginning with Marconi. As I said, we haven't collectively been doing enough fundamental research. And as a result, the candidates we have for 6G are not necessarily surefire, okay? The optimistic thing is, however, just looking at my discussion of superdirectivity, any existing wireless system is not operating anywhere near limits imposed by nature. So I'm going to stop here now and take some questions. Thank you.
Okay, thank you.